Hello, today I will be demonstrating how to use the Chiplytics power spectrum analysis system. We'll first start off by just loading a series of 10 chips. Today we'll be looking at the TC74HC02 APF, which is a series of quad 2-input NOR gates manufactured by Toshiba. And then we will also briefly compare a Texas Instruments fabricated SN74HC02N chip. So it's the same quad 2-input NOR chip. And we will test all of those with the Chiplytics power spectrum analysis system. Now, to get started, we will open the Chiplytics app, which I have here. That will take a couple of moments for the app to load. And during that process, you'll notice that the system is powered with a 5-volt supply. However, I've left the USB-C disconnected from the computer I'll be using just to demonstrate how to properly connect the Chiplytics PSA system to whatever computer device that you'll be using. So it should take another moment or two here for the actual application to open up. Today we'll be doing an offline directory as opposed to an online directory. The difference between the two is whether or not the data will be stored in the cloud or not, which can change its level of accessibility. So now that the Chiplytics application is loaded, the first thing we need to actually do is set an offline directory. So we'll do that by first going up into the Tools tab and click on the Set Offline Directory. When that happens, a file browser will pop up. We'll scroll to where we want to set the offline directory. In this case, I will set it in my desktop, select the folder, and at this point, the Chiplytics application will have set that offline directory for use. Now, I can continue offline by just clicking the Continue Offline button, and we'll open up on the Analysis tab. This is a brand new install of the Chiplytics PSA desktop application, so as expected, there are no analyses to show in this particular tab. But from this tab, we can actually connect the Chiplytics PSA system. And we can do that by clicking the Chiplytics disconnected status bar down at the bottom, which will bring up the device manager window. Now, by actually putting the USB-C into the Chiplytics PSA device, the device can auto-connect to the computer. If it doesn't wind up auto-connecting, just click the connect button. And at that point, the status should change to connected if done properly. The serial number of the device should show up along with the temperature, the current being supplied by the computer, and the auxiliary voltage. And at this point, you can click the Done button. At this point, you can see that the status has changed to Chiplytics is connected. Now, to actually go and connect some analyses, we're going to first go to the Parts tab. So as I mentioned, we'd first be looking at some TC74HC02 APF parts. In order to do that, we're going to click on the plus sign to add that part. In the manufacturer part number, that's going to be TC74HC02 APF. The manufacturer, as I mentioned before, is Toshiba. This is going to be a DIP package with 14 pins, and the vendor in this particular case is DigiKey. However, any other vendor can be added here, including Mouser, Arrow, or someone else. In this particular case, the date code is not applicable, so I'll add in NA. And now I can actually go and set the test configuration, which is going to determine what tests the PSA system will run. So we'll click on the plus sign there. We can name the test in this configuration line. I'll call this the 3-volt demo test. A description can be added if desired. However, in this case, I don't need to. And then we're going to set the actual test sequence. So the 1 is the first test that will be run. So I'll click on the plus sign to add that test. Now we can name basically this test. In this case, I'll call it the 3-volt test. And now we need to tell the PSA system which pin on the ZIF socket will actually have that voltage signal applied. In this case, with the way I'll be mounting it, it will be the 40th pin of the ZIF socket that will have the signal applied to it, and the grounded pin will be the 7th pin. I can additionally control, so you can set multiple pins to receive the signal, and you can set multiple pins to receive the grounded signal. I can also set the frequency at which the square wave is going to be applied. So we're going to use a 100 kilohertz frequency square wave. and then I can set the amplitude of that square wave. Now it's important to clarify that this is the peak-to-peak amplitude and it's referenced to 0 volts. So if I put in 2 here, then the maximum voltage seen by the device should be about 2 volts, and the minimum voltage seen by the device will be about 0 volts. There can be some ringing, which can lead to mild overshoot in both of these cases, so that's something that's important to note. Since we're going to be doing a 3-volt test, I will set the amplitude to be 3 volts. If I wanted to add a second test that will be run in conjunction with this test, I could click on the plus sign and fill out all of these different table values again, cell values again, and that would allow me to set up a second test to run sequentially. Now that I've done that, I can also set the sampling frequency, which will not vary between all of these tests. So in this case, I'm going to use 33.33 megahertz. You can choose a sampling frequency all the way up to 100 megahertz. I'm going to set the number of data points that will be collected per signal capture. So that'll be 4,000 data points. And then I can set the number of captures that will be averaged into a single signal. So in this case, I'll use 50. Additionally, I can set if I want to capture more than a single series of 50 captures per device. And I would do that by setting samples per unit to something other than 1. So if I set samples per unit to 1, 50 captures will be averaged, and that will be the output result. If I want more than that, so I can compare multiple captures of each device, I can set that to something like 2, 3, etc. At this point, this test configuration is ready to go. I can click the Save button, and at this point, we're ready to begin testing. So to begin testing the device, I can go to the Analyses tab. I can click on the New Analysis button. In this case, I will call this the Demo Analysis. And once again, I can add a description if so desired. I'll click on Save, and now I can open the analysis I've just created, which should be an empty analysis. In the Center tab, you'll see the results of Principal Component Analysis, which at this point should not have any data values as nothing has been captured, and you can see the actual signatures of each unit in this right tab. To actually capture data, I'm going to click on the Capture Signature Set button. I can start typing in part number, the part number that we just added, and all of the rest of the fields should auto-populate. If there were date codes that I'd specified, I could go ahead and select them here. Additionally, I can do the same with the vendor, which in this case is DigiKey. And finally, in configuration, I can select the actual test configuration that'll be used. And finally, I can add any labels or descriptions I'd like to add to this particular test series or device itself. Now I can click the Begin button, and this adds a signature set to the actual analysis. So to actually test the device, I'm going to click on the plus sign, which will bring up the Capture Signatures window. And at this point, we need to load our actual device. So I'm going to go ahead and do that by first removing the devices from their container. And now I can use a vacuum pen to actually move the device from the ESD mat into the ZIF socket. Once the device is in the ZIF socket, I will lower the latch, which should firmly secure the device. I can release the device, and at this point, we're ready to begin testing. In order to test the device, I'll click on the Capture button. Originally, the PSA system will capture a series of null signatures, which is effectively what the device response is with all of the relays closed. So effectively, you're not really probing the device in the null signatures, you're probing the system itself. Then, after it's completed capturing the null signatures for the first capture series of a signature set, it will go ahead and capture the actual device spectra. It's going to take the 3 individual test measurements that it's made and plot those on the PCA chart, which you can see they're well described by the Principal Component 1 and Principal Component 2. And finally, on the right-hand side, you can see the actual unit signatures compared. In this case, they're being compared against the null signature. Now, I can go ahead and capture the signature for Unit 2. I'll do that by first releasing the ZIF socket latch. I will take the device and remove it, and I can put on the second of the TC74HC02APF devices that we have. I will place that device back into the ZIF socket, making sure that it is properly loaded. And I will close the latch to secure the device in place. Now that the second device has been loaded, I can click the capture button again, and the PSA system will capture the signature of the second device in the series. It doesn't recapture the null signature, is the important thing to note. And so at this point, you'll see that the PCA graph has actually been updated with the new set of signatures captured from Unit 2. And the unit signature pane has been updated with the response of the Unit 2 to the actual pulse sequence that has been applied. Now I can go ahead and remove Unit 2, and now we will probably speed up to capture the rest of the units in this series. Okay, at this point, all 10 of the signatures have been captured. Any individual signature can both be seen by hovering over some of the data points in the PCA chart. So this one shows that it's Unit 7, and it's the first of the 3 tests performed on Unit 7. Additionally, you can go, and in the signature set window, you can click on a particular unit, and that will highlight that unit's response in the principal component analysis graph by demarcating that particular unit's response with X's rather than the typical circles. Additionally, as you can see, as I click on different units in the right pane, the signature response will change slightly depending on whether there was a specific amount of noise or something else picked up, or just slight variations between each set of devices. Finally, just to show an example of how the combination of power spectrum analysis and principal component analysis really are effective at differentiating different devices, I will take another device, which I need to first set up in the Parts tab. So this second device is the SN74HC02N, which is manufactured by Texas Instruments. It also is a DIP with 14 pins. We also received this device from DigiKey, and the date code is still not applicable. And finally, we will do another 3-volt demo. So now I will go and populate all of the fields of the test itself. So we're going to apply that voltage on the 40th pin of the ZIF socket. We will apply ground to the 7th pin. The frequency will remain at 100 kilohertz of the square wave. The amplitude of the square wave, or the peak-to-peak amplitude of the square wave, will be 3 volts. We'll still use a sampling frequency of 33.33, still use 4,000 data points per capture. We'll still average 50 captures to actually make our signature. And finally, we will still do an additional 3 samples per each unit tested. So now I'm going to save this device, and at this point I can go back to the Analyses tab. I can add a new signature set, which is going to be for the SN74HC02N part. I can click on the vendor, set that to DigiKey, and I don't need to set a label or description in this particular time. Now I can do the same process of clicking the plus sign, and now I can actually load the first SN74HC02N part. So as I mentioned at the beginning of this video, this is also a quad 2-input NOR chip, and it's instead manufactured by Texas Instruments rather than being manufactured by Toshiba. So at this point, the part is loaded. We can click the capture button. First, the PSA device will capture the null signatures, and next it will capture the actual 3-volt signature. Now what you'll immediately notice after capturing this is that the TC74HC02APF, so the NOR gates manufactured by Toshiba, are highly separated from the new data set that I just took for the SN74HC02N, so the quad 2 input NOR gate manufactured by Texas Instruments. And we expect this to be the case as these two devices were made by two different companies, and the different fabrication processes have enough variation that power spectrum analysis should be able to pick up on those differences. And that's exactly what's being represented here in this principal component analysis plot. At this point, I've showed you the basics of how to use the Chiplytics PSA desktop application, and also how to load, remove, and test parts on the Chiplytics power spectrum analysis device. Thank you for watching.